Hey, welcome back. In case you're thinking you clicked on the wrong video right now, there's actually a reason we're looking at this ship. Something I bought came in one of these containers, and to give you a hint, it weighs almost a metric ton and it has exactly 500 holes in it. But since you read the title, you already know it's a welding table. So in this video I'm going to show you the unboxing and setup and demonstrate some of the features and applications of this type of table, and we're also going to take some measurements and talk a little bit about precision and flatness. If you've been following my Instagram stories, you might have seen the journey that this thing has been on, because I was tracking this ship online for weeks. I actually ordered this table from a company called Kowosu in China and had it shipped over here to Europe. I know that sounds a little crazy at first, but they gave me a really good deal, and even with the shipping cost included, it ended up being a lot cheaper than buying a similar table from a local company, which I simply would not have been able to afford anytime soon. But that being said, I had to save up for this one a pretty long time too. Since my shop just happens to be right in one of the largest industrial ports in Europe, the ship basically arrived at my doorstep, which reduced the overall shipping cost. And that's also why I was able to shoot the footage you're looking at. So while I'm unpacking this extremely well-built shipping box, let me tell you a little about the contents. The table also came with a whole bunch of accessories, which are really the thing that make this useful beyond just being a table. And I'm going to show you what those do and why the table looks like Swiss cheese in a bit. I expect people will be asking about weight and dimensions, so I'm putting up some numbers here for you. Considering the weight of this thing, the scariest part was putting the legs under it, because it meant I had to lift the tabletop up into the air somehow. To get started with that, I had to jack up the pallet a bit so that my engine hoist has enough clearance to fit under the pallet. So I used a pallet jack and some wooden beams to raise it up a few centimeters. I'm going to use these lifting straps to pull it up. These are rated for 1 ton each. But in the configuration I'm going to use them in, they should hold about 140% of that. So that would be about 2.8 tons in total, which should be well within a safe range. Luckily these straps managed to fit into the holes on the table, so I just looped them through the bottom, and I made this quick hook tool to pull them up so that I don't have to reach underneath the table and risk losing my arm if it was to fall down. The green strap is rated for 2 tons, so when you put it in a loop, that doubles to 4 tons. Now I can get the hydraulic crane under the pallet. This thing is rated for 2 tons max, depending on how far you extend this boom out. And just to be on the safe side, I'm putting this at the 1.5 ton position, because that gives me enough reach, and with a cheap equipment like this you want to avoid pushing it to the limit. Attaching the legs with the table just hanging there was pretty scary and also a little challenging, but it worked out just fine in the end. Some people are gonna comment I should be wearing steel-toed boots for this, but I honestly doubt that if this was to fall on my foot, it would make any difference what kind of shoe I'm wearing. By the way, these legs are pretty heavy duty, and so are the casters, which are cast iron wheels with ball bearings, but I'm most likely going to switch all the legs out for new ones without casters, because I don't plan on moving this table around a lot. Quick service announcement: if you enjoyed this content and want to support this channel, you can join my Patreon, or you can also get one of these shirts that I designed, and there's a link to both of those in the description. The last important step for setting this table up is to level it. Even with this thing being so massive, or actually because of it, it can distort under its own weight. So if one leg is higher than the others, it can twist the tabletop, which is going to impact the overall flatness. And being flat is kind of the whole point here. So I'm starting out with just a regular water level, checking both the X and Y axis of the table, and since my floor is quite a bit higher towards the windows, it took a while to adjust it. Once I had the normal level dialed in, I switched over to this thing, which is a precision water level, and this is usually used to level machines like the mill and lathe. Now this thing is so ridiculously accurate that it can drive you insane. As you can see, it measures down to 0.02 millimeters over a meter, which means the slightest change can make this bubble move all over the place. I'm not going to make the table perfectly level with this. With this level, if both ends of the bubble are even inside the window, you're already doing pretty good. Speaking of measuring stuff, let's address the whole flatness thing for a second. Right now you're seeing some old footage of me building my first welding table, which is still in my shop, although I now just use it as more of a general workbench, but it's still a good example for a basic DIY welding table. I'm using the term basic because this really is essentially just a metal table. It's a frame made from steel tubing with your average rolled mild steel plates on top, so it was fairly affordable and easy to make. The main features of a table like this as far as welding goes are it doesn't catch on fire and it's conductive, so you can put your ground clamp on it. And compared to the new table, that's about as far as the similarities go. Now this kind of table is perfectly fine to build some basic stuff within some limitations, and after all, half my shop was built on this. But like most DIY tables or cheaper welding tables, there's something it lacks, which is precision. To demonstrate what I mean, I bought this straight edge. This looks like just a piece of flat bar, but it's actually a measuring instrument that has been precision ground to be extremely straight. One way to use this to check flatness is in combination with these feeler gauges. These are just strips of metal with the known thickness. In this set they go from 1 millimeter all the way down to 5/100. So when I start trying to slide different ones underneath the straight edge, I can determine variations in height of the surface below. Now let's take my old welding table as an example. I already know these plates are not flat in relation to each other, but even if we look only at one single plate, it's way less flat than you might expect, with a height difference of almost 0.8 millimeters within one plate. This is most likely not due to how the table was built, but simply a property of the raw materials, because these hot-rolled steel plates are way less flat than people often assume. If we try the same thing with my general purpose workbench here, which has a tabletop made from laminated plywood, it gets even worse. The surface drops significantly all around the outer perimeter, in some areas as much as 2 millimeters. This is not at all unusual for a sheet of plywood, and also not really a problem since I don't use this for precision work, but it's just interesting to know to put things in perspective. I want to give you two more quick examples. This is my table saw, which has a top made of cast iron that's been ground flat. As expected, this performs much better. I can only measure about 1/10 of deviation here. And one last example, this is my surface plate, whose only purpose it is to be as flat as possible to provide a reference surface for measuring things. This is actually a fairly cheap surface plate, and even this one has a tolerance rating within 3 or 4 micron. That's thousandths of a millimeter. To put that in perspective, a human hair is about 70 microns thick, and unsurprisingly, if I place the straight edge on here, I can't even slide the 500 gauge in there, because we're likely looking at a deviation in the micron range. So now that we've determined that nothing is ever really flat and that most stuff is less flat than you would think, let's check how flat the new welding table actually is. Now keep in mind, it's still a welding table and not a surface plate. It's made of steel, which likes to bend and twist, and it's very large, so there's a certain limit to how flat you can manufacture something like this. I started with the 0.1 millimeter gauge, and all around the outside I couldn't get that in anywhere. However, the closer you get to the center of the table, the larger the deviation becomes, which is to be expected since the center is the least supported area, so the table basically has a slight dish in the middle. At the lowest point I could determine, the largest gauge I could get in was 0.3 millimeters. Now my straight edge isn't long enough to cover the entire table, but based on this measurement and the fact that the surface is very even toward the outside, I think about 0.35 millimeter from corner to corner would be quite realistic, and that's actually almost exactly the tolerance rating that the manufacturer gave me, so that's good to know. What you also have to keep in mind here is that 0.3 of deviation over this entire surface has way less of a practical impact than the same deviation over, let's say, 50 centimeters. So you always have to put these measurements in perspective with the length that you're measuring over. Now, precision is of course a very relative concept, and what one person might consider crooked might look perfectly straight to someone else. So what I'm doing here might look like nitpicking to a hobbyist woodworker, whereas a precision machinist is probably going to think the table still isn't flat enough. So how you interpret these numbers also depends on your expectations and the kind of work you're doing. That being said, I think there's actually a way to even improve this number, because the table has mounting points for 2 additional legs in the middle. So by putting adjustable legs on those, which I'll do in the future, I'm pretty sure it will be possible to adjust this by another 1/10 or so. By the way, if you're further interested in this topic, there's a really good video by Fireball Tool where Jason tests all kinds of different models and styles of welding tables and compares their precision. Since that was a big help for me, I'm going to put a link to that in the description. Since this is a 3D welding table, that allows you to clamp things onto the sides of it too. So one other thing that's relevant is how square the sides are to the top. And upon checking that, I couldn't find any spot that is out of square in any way that I can measure. So overall, I'm really happy with the accuracy of this table and knowing that I can rely on it. Now, after all that theoretical stuff, let's get practical and check out some of the tooling I got for this. Basically, you can think of this as a huge set of Legos, meaning there's an endless number of ways in which you can utilize and combine all of these accessories. And I also only have a basic set here. There's many more and also much bigger fixtures you can buy for these tables. I'll just give you some basic examples to illustrate the overall concept. The main way to attach tooling to the table are these bolts, and they're actually a really cool design. The way it works is there's a screw inside that you can screw in by turning the top. That pushes these steel balls outwards. To use them, you simply put them into one of the holes and screw them in, and they pretty much act like a normal screw. They have a surprising amount of holding power, so even just tightening them by hand holds stuff pretty securely, but if you want to, you can also use an Allen key. To better illustrate how this works, I'm just going to attach these two pieces together. These have the same thickness and the same chamfer as the tabletop. So this is essentially what's happening on the bottom of the table. When you screw the top in, there's two things happening. One is that the lower part of the bolt gets pulled up, and at the same time the steel balls get pushed outwards and engage in the chamfered edge of the hole. You might ask, why don't they just cut threads into the table and use normal screws? And the main reason is that with this solution you can repeat the fastening process pretty much endlessly, while threads, even in steel, will start to wear out and become loose over time. So with this method, the system maintains its accuracy over a long time. Okay, so what you mostly use this stuff for is to create stops to align and position your work on the table. Since the grid of holes on here has been machined with the same accuracy as the rest of the table, that means all of these holes represent perfectly parallel lines between them, and intersecting lines represent a perfect 90-degree angle. So you can basically think of the table as a giant 3-dimensional sheet of graph paper that you can clamp and weld things on. So if I align a workpiece to these stops, I can now be sure that it runs straight along the table. Thanks to these long holes, you can also use these as adjustable stops. For example, to hold this piece of tubing against the other stop. And already this simple setup is something that would be a big help. For example, if you're making many of the same workpiece, because you can just swap tubing in and out and it's automatically aligned every time. This is probably the most common use, If you just place two of these perpendicular to each other, you get a very quick way to construct something at a right angle. And there's also another way of doing this by clamping stops to the side of the table. Now let's look at the main feature, which is clamping. The table came with a whole selection of different clamps for different purposes. These are the most basic ones, which are just like your average C-clamp, except they clamp downwards. Then there's also this design where you can adjust the swing of the clamp depending on how far your workpiece is from the next available hole. Another reason why these are cool is you kind of get two clamps in one, because you can pull out the top and use it as a sideways clamp. And since all the diameters match on all this tooling, you can also attach these to other tooling. So like I said, the possibilities are almost endless. Another design are these 45-degree clamps, and these are great because they clamp in two directions at once. So if you want to clamp a workpiece down and also against something, you only need one clamp to do it. Now that I got this clamped up, I'm just going to weld it to show you what the whole point of all this clamping is. Because what it does is it greatly limits welding distortion, which is always a problem when you're welding. The material moves around and warps when it melts and cools down again. And there's a lot of ways to deal with that, but if you hold your parts really tightly, it greatly reduces the chances of your part coming out crooked, and it also speeds up the work by a lot, because you can spend less time double checking and fixing stuff. So even though this looks like a lot of setup work, it's way quicker in the end. Yeah, those welds definitely aren't my proudest work, but the point I'm making here is that the part came out perfectly square, even though I didn't place any tack welds. Okay, now let's assume we want to attach a vertical piece to this part. That's what these angle pieces are for. Ideally, you would also put another one of these somewhere, but you get the general idea. And of course, you can also combine all this stuff with the regular old ways of clamping, like a classic C-clamp. I'm going to keep using the same workpiece here for demonstration purposes, but just imagine this was some kind of complex construction that extends downwards and upwards. We can now add a whole dimension to this thing, because you can also clamp and align things on the side of the table. And again, if we check from the top now, everything you add on from here will also be square to the rest. Of course, you can also use the grid to set up angles. So for example, this would be a 45-degree inside corner. And for the opposite corner, you just flip this around. So again, there's no measuring or double checking involved. You can also set up a custom angle. There's special fixtures that make this even easier, but together with the clamp, it also works with these simple stops. Like I said, all the accessories can also be combined with each other, and these angle brackets can also be used for something else. When you attach these to the side, you get an extension that sits flush with the tabletop and allows you to increase your effective work area. Of course, this works even better with bigger angle pieces. As you saw, the tabletop also has a scale engraved, so if you put a stop in the corner, you can use that for positioning and measuring parts. And the same scale is also on the stop blocks, which is pretty cool because it corresponds to the grid on the table. So if I set this to 50, for example, and then put a 50mm piece of tubing here, it's going to be aligned with the grid. Last item I got here are these V-blocks. These are for round workpieces like tubing, and they make sure it sits on the center line when you clamp it down. And that's also why the feet on these clamps have this groove in them. That's so the foot doesn't slide off of round objects when you tighten the clamp, which I'm sure we've all experienced with normal C-clamps. And once again, you can combine these blocks with other parts too. For example, if you wanted to clamp this tubing up vertically. There's one last thing I want to show you. This table actually has a luxury feature, which is it's been hardened by a process called plasma nitriding to make the surface super tough. And to demonstrate what that means, I got a piece of mild steel flat bar here, so let's give my old welding table a beating with that. So both the table and the flat bar got pretty banged up. Now I'm using the edge to do a little scratch test to see how easily the surface gets worn. And yes, I'm crazy, so I'm gonna do the same thing to my new table. What looks like damage right here is actually just some discolorations that you can just wipe off. You can see the mill scale being chipped off the flat bar here, but the edge of the table actually hasn't taken any functional damage. Same with the scratch test here, it's pretty much not leaving any mark, so I'm pretty sure this table is gonna hold up for a long time. Okay, that's it for this one. I hope I could shed some light on this topic for you, and if you want to see more examples of all the ways to utilize a table like this, it's most likely going to see some use in pretty much all of my projects from now on. So if you liked the video, be sure to subscribe. And also, thanks for watching and see you next time.